Currently, our knowledge of dark matter is what deserves the most attention, as it is still one of the most mysterious elements in our universe, yet also one of the most important. According to the most accurate cosmological simulations we have to date, dark matter is said to make up about 27% of the observable universe. And though we can't see it, we can deduce its existence from the way it affects the nearby baryonic matter. Confused? Don't worry, continue watching, and you will understand how much impact black matter has on the entire existence of the cosmos. Also, how we have before now understood dark matter and why it may all be so flawed. A large chunk of our knowledge regarding this unknown part of the cosmos comes from the groundbreaking model developed in the late 1990s. The LCDM model, an acronym for Lambda Cold Dark Matter, has been the most effective cosmological model to date. This simulation makes an important claim about dark matter, proposing that the formation of the massive galaxies we see today was significantly aided by cold dark particles. These speculations have gone unconfirmed for a long time because we didn't have the resources to carry out the required studies. But now, the earliest billion years and the last unexplored period in the history of the universe are readily accessible thanks to the James Webb Space Telescope. The first studies of dark matter have finally been done by Webb, and the findings may well usher us into a whole new era in physics and astronomy. The earliest galaxies found by the telescope in its early release science program offered a chance to put the LCDM model's predictions to the test. But in a shocking twist of events, the outcomes deduced were totally unexpected. In fact, the results have questioned our supposed knowledge of dark matter and how we once thought the universe was formed. The LCDM model makes predictions about how galaxies originate, and it emphasizes the importance of cold dark matter in this process. Different types of dark matter are thought to exist, and the classifications range from cold to warm and then hot. These categories were proposed by researchers as a way to describe the speed at which the particles of dark matter can move. The massive particles that make up cold dark matter are believed to have extremely slow and insignificant speeds. Light particles that make up hot dark matter, on the other hand, move at ultra-relativistic speeds. That is, the particles move almost at the speed of light. And lastly, warm dark matter, which has intermediate mass and velocity, lies between this previous two. Astronomers believe that large-scale structures in space were formed from the combination of any or all of the three dark matter particles. According to the available models, heated dark matter flows so quickly that it will only flatten out the structures. As a result, it is not very helpful in gathering matter for galaxy formation. But then it comes to the sluggish motion of cold dark matter. It allows a combination with other particles to create gravitational wells, which aid in the formation of galaxies. Warm dark matter, which exhibits intermediate qualities, is also important in the formation of galaxies. But the structures it produces are believed to be different from those produced by the cold ones due to the lighter weight of its particles. Moving on, it just turns out that the most distant galaxies found by Webb were entirely different from what we had anticipated. Three key aspects regarding these early galaxies should, however, be noted. Number one, the rate at which these galaxies created stars is significantly higher than what we would anticipate for the early cosmos. Two, they have an extreme redshift of over 11. Redshifts are used by astronomers to gauge the universe's expansion and consequently to calculate the separation between the oldest and most distant objects in our universe. So these galaxies must have formed within the first 500 million years following the Big Bang, making them one of the earliest bunch. Last but not least, they have a substantial stellar mass of about 1 billion solar masses, with simulations indicating that galaxy formation takes roughly 1 billion years. These results indicate something very perplexing that we are yet to understand. Scientists are even speculating that it must be groups of proto-galaxies that are in the process of merging into larger galaxies that we were observing. Despite these theories, they still don't explain why we are seeing completely formed galaxies just within the first few 100 million years after the Big Bang. While the near cosmos does not provide enough details to discern which particles were involved, the first billion years of the universe are the only place where we hope to find answers. We can use Webb's observations of extremely redshifted galaxies to comprehend dark matter's makeup and its function in the development of these massive structures. One of the parameters used by scientists was redshift. Since redshifts are a measure of distance, then it can be deduced that the greater the redshift, the farther away a galaxy is from us. A plot of the density of star formation rate versus redshift was also used. Star formation rate plays a key role in galactic and interstellar astronomy. It is usually measured in solar masses per year and provides information on how quickly stars are produced from dust and gas. Therefore, the star formation density represents the rate of star formation per unit volume. Researchers then went further to analyze the densities of the observed galaxies spread over the UV luminosity. This was done across several warm and cool dark matter theories, as well as the mass distribution of these galaxies. It was then discovered that the high redshift galaxies can only be described by cold dark matter models when these values were plotted for Webb galaxies. In fact, these findings suggest that the galaxy formation in distant high redshift galaxies could still be influenced by cold dark matter. So, due to their inability to accurately forecast the development of these galaxies, warm dark matter models were disregarded with respect to the known rates of the formation of the stars in these galaxies. This was a huge leap in our discovery, as it proves that the previous theories regarding the makeup of the dark matter that was involved in the buildup of these galaxies were correct. However, there is currently a major issue with the LCDM model. Although it was correct about the nature of the matter present in those galaxies, its predictions concerning the characteristics of high redshift galaxies were not. Note, however, that the discrepancies in these results do not infer that the Big Bang didn't happen because there are large amounts of data that completely supports the theory. It's just that any new explanation that will successfully shed light on Webb's findings and the universe's creation must also fit with the Big Bang's predictions. The LCDM model does not predict that these early galaxies would possess characteristics like high absolute UV magnitudes, high stellar mass, and high star formation rate. This could be because dark matter had an important role in the early few 100 million years of the universe, a role that we still don't fully comprehend. The importance of preserving the idea of dark matter cannot be overstated, or else our current model of cosmology, which has been accurate until now, would collapse in the absence of this theory. The LCDM model, which took years to create, can be saved if we can correct it to clarify the characteristics of the galaxies in the early universe captured by Webb. Otherwise, we would eventually need to develop a new theory, and we would find ourselves starting over. So, many rests on the outcome of the discussion surrounding the nature of dark matter. Like this video and subscribe to the channel. We would love to have you again. Thanks for watching.